I got a real quick, actually, let me share my screen. I didn't even have to log in. That was kind of cool. Okay, so happy Thursday. It is week 9, Thursday, week 9. This looks like a lot, and it is kind of a lot, but let me explain what's going on here. So we're going to do 9.2 today. So 9.2 is we did point estimates, sorry. We did confidence intervals with proportions on Tuesday. Today we're going to do confidence intervals with mean. So a lot of it's the same, but we're going to be learning about the back side of the Z table. So if you have your Z table, we're going to be flipping it over. We're going to be using the back side of it. So table 6 instead of table 5. So hopefully you've printed it two-sided if you have it printed, because we're going to be using the back side today. And so that's t-values. We're going to talk about what t-values are. We're going to talk about building a confidence interval for a population mean, and we're going to determine the sample size. After that, we're going to do lab 5 together. So I'm going to put all of this in one. That's normally what I would teach on this day, but because we don't have class next week, Thursday, after lab 5, I'm going to go into section 10.1. 10.1 does not have any math involved. It's mostly like vocabulary and some kind of laying groundwork for hypothesis testing. If you want to, you're more than welcome to just leave after lab 5. And then when you're ready to jump into chapter 10, you can just watch the video. It will not hurt my feelings if you do that. Will not hurt my feelings at all if you jump out after lab 5. So just letting you know. There's a lot of screens that we go through quickly, and so that's why we have 58 slides, but there's a lot of screens that we go through pretty quickly. And kind of like when we have graphs and things that we're just like, oh yeah, look at this. This is interesting. Let's go to the next screen. So we'll also be learning a new calculator function today. So hopefully you have your fancy schmancy calculator with you because we will be learning a new calculator function today. So in 10.1, we're looking at how to set up a hypothesis test as far as the very beginning, showing what a null and alternative hypothesis is. We're going to be looking at what type 1 and type 2 errors are, and then what a conclusion to a hypothesis test look like. We're not doing any of the math in the middle. That's what we're doing on Monday. So none of the math, or sorry, Tuesday, none of the math in the middle. We're just going to look at how to set up the intro and how to write the hypothesis test. So that's today. It's a lot. It's going to be fun. Of course, it's going to be fun. We're all hanging out here together. Of course, it's going to be fun. All right. So we already talked about point estimates with proportions. So for a mean, we use the sample mean for our point estimate. So you're going to have a sample and you're going to find the mean of that sample, and that is your point estimate. So if it asks you to find the point estimate, all you're doing is finding the mean of the sample. And we use this point estimate to estimate the population mean, or mu. So we use our confidence intervals when we don't know the actual mean of a population. And so we take our sample mean and we set up our confidence interval. The same thing we did with proportion. Things are just going to look just a little bit different here. We will still be using the same standard deviation that we used with sampling distributions in chapter 8. I think that's my next screen. Nope, it's not. So that, remember, sigma divided by square root of n, it'll look slightly different, but we're still going to be using that. All right. So here is a whole bunch of pennies. I think we did pennies previously. So these pennies are minted after 1982. They're made from 97.5% zinc and 2.5% copper. This data represents the weight in grams of 17 randomly selected pennies. So this is a simple random sample. This is all the weights. So to get my point estimate, I just calculate that mean. The sample mean here, my X bar is 2.464. So for our confidence interval, we would use 2.464 to estimate the population mean. So we always, when we're using our raw data, we round to 1 decimal point farther than the raw data once it is. So our raw data here goes to the 100th. we would round to the thousandths. Now, my open math will tell you what they want, but if you are doing your own, like if you are doing your own thing, you're doing, final project or whatever, just round to one farther. That's just, or when you're out in the wild and you're creating your own data and doing your own analysis in the world for whatever job you have, we generally just round to one decimal place farther. But I don't think anyone's going to get mad at you if you do something different out in the wild after this class. All right. So let me explain a t distribution. So we use a t distribution when we don't know information about the population. We do this when we have smaller sample sizes generally. In this class, if we're dealing with the confidence intervals for mean or hypothesis tests for mean, we will just use t distributions instead of z. So we're going to use t values instead of z values. They basically have the same meaning, but as I said, we use t values generally when we have a smaller sample size and when we don't know all of the information about the population. So to find a t value, like it's kind of like a z-score. So we're finding a t-score. You take this is the sample mean. You take the sample mean, subtract it from the population mean if you have it, and then you divide it by, this is the new standard deviation. So it's just like finding a z-score, but it is a t-score. Now, don't worry about n minus 1 degrees of freedom yet. We will talk about that in a few minutes. We will be using n minus 1 degrees of freedom, but don't worry about that. I believe back when I taught you about standard deviation and we divided by n minus 1, I said the exact same words. Don't worry about it yet. Very soon we'll be worrying about it. It's not a big deal. It's nothing to be scared about. So we're good. Nothing to be scared about. All right. Pop over here. So generally, if we know the population standard deviation, we usually will use the z-scores. But as I said, we are going to we're going to be using, if we're dealing with mean, we're going to use t-values. If we're dealing with proportions, we'll use z-values. Try and just do that. Don't worry about when we use which. I'm not going to ask you when we use which. I'm going to show you the difference between a t-value and a z-value, or z-score and a t-score with a histogram. So let me show you what it looks like. So here's my histogram for z. It's nice and pretty. It's bell-shaped. It's all pretty compact right there around the middle. Here's my histogram for t. Notice with the t, we are more spread out in the tails here. It happens a lot because we have smaller sample sizes. Because remember when we talked about how the mean is normally distributed if the population is normally distributed, or if we have larger sample sizes. When our sample sizes are smaller, we tend to get these long tails. Yes, they're still even on both sides, so we're symmetric, but there's usually a little bit more in the tails when we're dealing with z-scores or t-scores. Once again, you are not going to have to give this information back to me. I'm not going to ask you what's the difference or anything like that. Okay. So conclusion, we have Z follows a normal distribution, symmetric about the mean. Most of it's between -3 and 3, and it is or pretty much everything. And it is just a really nice, pretty tightly compact bell curve. The T distribution, it also is centered about 0, but it has the longer tails. It is also still symmetric. And a lot of times because we're using a sample standard deviation and a sample mean here, it tends to be a little bit more spread out. Not a big deal. It's perfect for our uses. Okay. T distribution is different for different degrees of freedom. So I'm going to underline this right here, put a star next to it. So it's a little more complicated than this, but this is an intro stats class. So this is what we're going to say. Degrees of freedom equals sample size. So every time I say degrees of freedom, think sample size. So our t values are going to be different for different sample sizes. So t distribution is centered about the mean or about 0. It is symmetric. The area under the curve is 1, just like it is with z. It has 50% above 0 and 50% below 0. And just like with everything else we've been dealing with, as it gets closer, as my x values or as my t gets super, super big and super, super small, it's going to approach 0, but it's never going to reach 0. We just have a little bit more in the tail. As I just said right here, area in the tail is a little bit greater than with Z distribution. It's because we're using samples and smaller sample sizes. As our sample size increases, as our sample size gets bigger and bigger, our curve for the T is going to get closer and closer to the same curve as we have with Z. It's going to get closer and closer because of the law of large numbers. As my sample sizes get bigger and bigger, it's going to approach Z. It's going to look more like Z. And it usually happens around, I know we say 30 is where it gets normal, but around 40 is kind of where we get the perfectly with Z. Our T values and Z values are basically the same when we get to about 40. It really depends on the population, but 40 is kind of a rule-ish of thumb. I will show you some examples in a little bit. All right, so take a look here. So our normal curve is the blue one. Smaller sample size is this orange one right here. Notice how the tail is fatter. And then when we use 15 for our sample size, the red one right here, so I'm going to put a blue arrow onto the red one. The red one right here, it is getting pretty close to the blue. It is getting closer and closer to that. Now, if I made my sample size even bigger, it's going to get closer and closer to the blue one. So I told you some of these we just whip right through because we're already on slide 14. So the notation for the t value is t sub alpha. We are going to be using, just like remember we did z sub alpha divided by 2, we're going to do t sub alpha divided by 2 for this. And also with t values, it gives us the area to the right, whereas z gives us the area to the left. I don't know why. This is just what they do. So alpha is just, I don't know if I mentioned this on, what day was this, on Tuesday or not. Alpha is just the difference between whatever our confidence level is and 100. So if we had our confidence level of 95% or 0.95, then our alpha would be 0.05. I think I mentioned that on Tuesday, but if I didn't, it warrants saying it again. Alrighty. Okay. I'm going to show you how to use the t-table now. So if you have your t-table, go ahead and flip it. So it's the table 6. It's the flip side of the z-table. So we're looking for, now we're not going to be doing this as alpha divided by 2. We're doing it just as alpha. So this one, it gives me notation like this. This notation right there that I just boxed, that means find your t value with 0.20 as the number that we're going to be looking for. So my alpha is 0.20, sorry, and we're using 10 degrees of freedom. So we're using a sample size of 10. So let's take a look at my Z table. Do I have our T table? Oh, I do have it on the other side, but I want to show you ours instead. So I'm going to scroll down to the T table. All right, make it a little bit bigger. Okay, actually, I think it might be better if do I still have it on here? There we go. I think it might be better to do it where I can actually write on it. So I'm gonna do it right here where I can write on it. All right. So on your T table, so this is table 6. On your T table, degrees of freedom is right here. It is on the left. The left column is the degrees of freedom. That is the sample size. So we're looking at a sample size of 10. So my sample size of 10 right here. I'll do this again. My sample size of 10 is right here. And I want the T value for 0.20. So you just notice how my column up at the top, I'm going to highlight it. My column up here at the top has all of the alphas. So I'm just looking for the alpha of 0.20. So I'm going to come down here and 0.20 alpha with 10 degrees of freedom. My T value is 0.879. That's my T value. So you find the alpha up at the top, degrees of freedom on the left column, and then just where they match up. That would be your alpha. Uh-oh, sorry about that. So I'm going to scroll down because I want to show you stuff that's happening down at the bottom here. So notice how, remember I told you that it was around 40 where my Z scores and my T scores become approximately the same. At 40 is when they just start jumping values here. Because those values are so super close, they start jumping. And I think we have an example later on where I'm going to show you what to do if we end up with like 45. But right now, just worry about finding this right here with that right there. Right. Let me go back up to the top here. Oh, now it's open right there. Good. All right. So, and I just lost it. It was 0.879. That was my T value. So they show it right here. Theirs looks a little bit different because they have one tail and two tail and thing like that, but very similar. They have their 10 and then 0.20 right here, 0.879. So that is our T value. So the T value has the same meaning, as it has the same meaning as the Z score. It would be a value that is 0.879 standard deviations away from your sample mean. Because remember, we're doing sample means here, we don't know the actual mean. So 0.879 is how many standard deviations we are away from that sample mean, or that value is. Any questions so far? All right. Okay. We're going to want to do this again. I'm going to show you fancy schmancy calculator here in a second. So I want you to find the T value that has the area under the T distribution. So we're looking at to the right of 0.05 with 15 degrees of freedom. I'll pop over in case you don't have your on you. So 0.05 is your alpha, 15 degrees of freedom. So I will open up the table. I'm going to erase things. I want you to see if you can find it. Let me make it a little bit bigger. 0.05, 15 degrees of freedom. All right, so 0.05 is right there. 15 degrees of freedom is right there. Therefore, where they meet up, right here, our T value, 1.753. Yep, good, 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 good. I see you in the chat. Yay! Okay. I'm going to show you how to do this on the calculator because now I believe the TI-83 does not have a calculator function to find the T value. I believe it does not, but the 84s do. So I'm going to show it to you. And if you have an 83, you're just going to have to use the T table because they're all there. But I'm still going to show you how to do it on the calculator. All right. So you go back to second vars because we're looking at a t distribution. So second vars, and down, notice how underneath inverse norm, we have inverse t. Inverse t right down here below inverse norm. So second vars, number 4 is inverse t. I want the area, we're going to do 0.05, which is the one we were just looking at, for 15 degrees of freedom. And remember, the area is to the right. Hit enter. If you don't have the fancy, like the menu thing that I have, it would be area and then degrees of freedom and hit enter. Oh, they do it to the left. That's very interesting. So I guess the calculator gives it to the left. You're just going to have to know which one you need, whether you need the positive or negative. So I probably should have put 0.95 in here. I was not aware that it did it to the left instead of to the right. Okay, but to the right, no big deal. All right. So inverse t in your calculator if you have it. If not, you can use your t table. Okay. Let's put these t values to work. All right. Confidence interval for mean. So we need to make sure that our sample data is random. They'll just say that it was randomly chosen. Now, if it doesn't say it was random, if you are doing, you're going to have to state that. Now, you don't have to state it in My Open Math, but if you were doing on your test, I would want you to say assuming random. So if it doesn't specifically say that it's random, we're going to assume it's random. The sample size has to be less than 5% of the population, and either the population has to be normally distributed or our sample size has to be 30 or greater. Now, if it's not 30 or greater and it doesn't say the population is normally distributed, then you're just going to assume normal because I want you to keep doing the math. So just tell me you're assuming it's normal. The way that we calculate our margin of error is basically the same as we calculated the margin of error previously. It just tiny little tweaks here and there. So we're going to use mean plus or minus. This right here is my margin of error. Okay. The critical value is going to be the t value for alpha divided by 2. So if my alpha is 0.05, you'll use 0.025. You divide it in half. Important thing here, I'm going to actually highlight this. Finally, the day is, we use n-1 degrees of freedom. So if your sample size is 15, you will use the critical value for 14 for your degrees of freedom. We do this because we're dealing with sample data. We need to account for the variation that occurs because we're dealing with sample data. The same thing when we were calculating sample standard deviation. So use sample size. Remember, that's not the right word. So you would do sample size minus 1. So use sample size minus 1 when you're finding your t-value. And then this right here, this is just that new standard deviation. I don't want to use that. I'm going to use a highlighter because highlighters are fun. So this is just your new standard deviation. The same thing we were doing with proportions, but with the ones for mean. Questions on this? Probably make more sense once we do the math. It always does, isn't it? Once we jump into the math, it's like, oh yeah, now it makes sense. So here we go. Okay, here we have this is our sample of pennies. We're going to construct a 99% confidence interval about the population mean for the weight in grams of pennies minted after 1982. This sample right here, this sample right here has a standard deviation of 0.02 and a sample mean of 2.464. So we don't actually have to find the sample standard deviation here. They just gave us the data. Now, in our calculator function, we're going to be able to do it either way, whether we have the data or without the data. And I'm going to show you how to do that, but not yet. Okay, so we're at 2, 4, 6, 8, 10, 12, 14, 16, 17. So 17 is less than 5% of our population. Absolutely. Um, it doesn't say that it's normally distributed. We're going to assume normal, and we're going to assume simple random sample. I think it said previously that it was a random sample, but it's not telling us that right now. So we're just assuming these things. So if it doesn't say it, we're just going to assume it because otherwise we wouldn't be able to do the work here. So next thing I'm going to do is I'm going to look for my T sub alpha divided by 2, 99% confidence interval. I do that up here. 1 minus 0.99 equals 0.01. So I take 0.01 divided by 2. I'm looking at 0.005. This is alpha divided by 2 right there. Okay, so we're going to use 0.005 and our sample size, n equals 17. But we're going to use 16 on our table. So I'm going to pop back over to the table. Okay. Come on, go away. Okay. We're using 0.005 because that's half of our alpha. So where is that? That's right here. 0.005. And we're going to use 1 less than our sample size. So degrees of freedom, n minus 1. So we're using 16. N minus 1 degrees of freedom. I'm coming right over here. Our t value is 2.921 because it's under the 0.005 and it's n minus 1 degrees of freedom. So we're using a t value of 2.921. Okay. Beautiful. Okay. Now I'm going to find the standard deviation. So we're using sigma sub x bar, which I think that they write it as S sub x bar, don't they? Or do they don't write it as anything? Okay, we're just going to continue calling it that. Okay, our sample standard deviation is 0.02 and our sample size is 17. Do not subtract 1 from your sample size here, only when finding your critical value. I'm going to label that critical value. So do not subtract 1 when you're finding the standard deviation. So I have approximately 0.00, I'm going to go to 49. Is that what you got? Seems right. I just wanted to make sure if anybody else is using their calculator that they got the same thing. Sometimes I just don't trust myself. Okay, let's calculate a margin of error. Margin of error equals, it's going to be the t sub alpha divided by 2 times our sigma sub x bar. So it's going to be 2.921 times 0.0049. This is going to be my margin of error. Zero 0.014. This is what we're going to use for our margin of error. There we go. So the way that we can answer this question, so we are estimating the population mean. That's what we're estimating. So I could either do X bar plus or minus margin of error. So it would be 2.464 plus or minus 0.014, or Or the other way is in the parentheses, subtract 0.014. So 2.450, and then add 0.12, 0.014, 2.478. Those are the two ways that you can write this. So I'm going to write the conclusion. We are 99% confident that the actual mean weight of pennies, and it should be pennies minted after 1982, but I'm not going to write all those words, is between 2.450 and 2.478 ounces. Make sure you put the units there. Make sure you refer specifically, like directly to the claim, and you use your units. What questions do you have at the moment? All right, jump to the next screen. This is just exactly what we just did. Those are the numbers we got. Amazing. We are 99% confident the mean weight of pennies minted after 1982 is between those two values. Those are the exact same two values we have. It's beautiful, beautiful, beautiful. I love when the answers are the same. Every once in a great while, I'll do something weird and I come over here and I'm like, wait, that's not the number I got. Just, your math teacher being human. All right. So we're going to, now if you have data values and they don't give you your mean and standard deviation, you're going to need to put this in your list and you're going to need to use one variable statistics or one var stats. Now, we're going to do our confidence interval here, and we're going to do it by hand. And then what I'm going to do is I'm going to put it into the list on my screen and use one var stats because we're going to come back and we're going to do this one in the calculator also. So I'm going to pop over to my calculator and put these values in. You probably want to put yours in also because we're going to use it for confidence interval in a couple minutes. Okay, so stat edit gives me my list one. I've got stuff in here, so I'm going to clear it out. Do not delete, hit clear. Been a while since we've used one variable statistics. All right, so I'm going to put these in here. Feel free to follow along or use your own list that you have printed out. $38.9. I didn't even look at what this story was about. Okay. Okay. Give you a second to get your numbers in there. Okay. We good? All right. Okay, so I have those in there now. Now I'm going to go over to stat, calc. We're just using one variable statistics. I don't want the frequency list. I'm going to clear that out. So just list one, hit calculate. Remember, we want the sample standard deviation because this is a sample. So our mean is 36.8, sample standard deviation 2.917. There we go. So we have that data, and I'm just going to leave this here and pop back over. Okay. So we have our mean and our standard deviation. That's good. We need that. This tells us, let's see here, it tells us it's a simple random sample. We are going to assume normal. Basically, we're assuming the population is normally distributed. I just don't want to write all of those words, but we are assuming the population is normally distributed. It tells us it's simple random sample. I usually do SRS and then just put a check mark next to it. Um, if you don't mention it, I'm not going to mark you down for it. But I usually, it's just because it's like the boxes I check as I go. And then how many do we have? 16. So 16 is less than 5% of drivers, I guess, of our population. All right. We got all that out of the way. That's fabulous. Okay. Now we need to find our T value. I'm going to give you a minute. We're going to figure out what the alpha is, and then I'm going to let you find it on your own before I do, because I think that's a good skill. So our alpha, 1 minus 0.95 equals 0.05. 0.05 divided by 2, this is alpha, equals 0.025. This is what you are using. And you're going to use n minus 1 degrees of freedom. So n minus 1 degrees of freedom is 15. So for your t value, use 15. Pop back over. Whoops, that's not where I want to be. Pop back to the t table. 0.025 and 15. Oh, look at you already having that there. You were locked and loaded, weren't you? Absolutely. 2.131 is what we're using. Perfect. So my T, oh, that's not a pen. I'm glad you put it in the chat also, because as soon as I navigated away from my T table, it left my brain. So in the chat, it's good that I can look back and see it. I don't know if that happens to any of y'all, but as soon as I navigate away from the number, I'm like, well, I don't know what that number is anymore. Okay. So our T, good. I'm glad it's not just me. 2.131. Good. That is our T value. What we're going, okay. Confidence intervals, we are not going to use negatives. No. We will use negatives when we get to hypothesis testing, but in 9.2, we will never use negatives. So if you use your calculator and you get a negative, just throw the negative away. It's going to be the same value. That was a great question. But for confidence intervals, we never use negatives for our z-scores or t-scores, either one. All right. Now we need our standard deviation. Let's go ahead and calculate that. Remember, you do not n minus 1 for your standard deviation. Use the 16. Do not n minus 1. All right. Doing okay so far? Yay, good. Yes, yes, yes. Woohoo. All right. Go ahead and calculate your margin of error. After we do this, I'm going to show you how to use what the calculator function is, and you'll be really happy. and you'll be thankful, but you got to know how to do it by hand first. There's just not enough room on this page. How'd we do? Did you guys get 1.55? All right. I don't really have room to write my whole, yes, yay. I don't have room to write my whole, I could do it up top. Okay. So we're going to use, we can either, once again, uh, since I have 36.8 for my mean, I think I'm going to just do 1.6 for my margin of error because my means to one decimal place. I know I'm being kind of lazy. Sometimes I'm lazy. I know that's new. I'm going to go to 1.6. Okay, so you could either say, I'm going to make some room here. Just make a box. Okay, you could either say 36.8 plus or minus 1.6. And that you would have to put, what is it, miles per gallon? MPG. So put the MPG there. Or you can, I'm going to make it another box. I'm going to put a box right here. Or you can actually do the math. I know I could do this math in my head, but for some reason, so 35.2 to 38.4. Either way, depending on what my open math tells you what to do. My open math will tell you what it wants you to do. I will also tell you what I want you to do on the test. I will be very, very clear what I'm looking for. Okay, we are, we're writing it up at the top, are 95% confident that the actual, so I want you to either say actual mean or the population mean, either one. So either use the words actual mean or use the words population mean. Mean miles per gallon. I'm not going to write all these words, but it's of a 2011 Ford Focus is between 35.2 and 38.4 miles per gallon. Questions on this? Guys want a calculator function? I'm going to pop over to the other screen. This right here is our calculator function. Stats. We go to stats just like we did before. Go over to tests and use T interval. This T interval I'm going to highlight because I love a good highlighter. I don't know about y'all, but I love a good highlighter. Okay, that is what we are using. So we already have our data in the calculator because we're thinking ahead like that, which is a really cool thing to do. So I'm going to pop back over to the calculator. Boom. And I'm going to clear this out. I'm going to show you how to use the T interval. Now there's two different ways. If you have all the data that you put in your list, or if they give you mean and standard deviation, it'll allow both of them. So I'll show you how this works. Go to stat, over to tests. T interval is right here. It's number 8. Hit enter. So it's You use the data if you have a list in L1. You use stats if it gives you a mean and a standard deviation. Right now, we're going to use data. It's our list is in L1. Leave frequency at 1 and put in what our confidence level is. Our confidence level is 95%. So we're good there. So data, wherever your list is, and then confidence level. Go down to calculate and hit enter. Isn't this beautiful? Is this the same numbers we got? I mean, I rounded, but still the same. We had 35.2 and 38.4. That's perfect. It's beautiful. And the standard deviation that it gives us is the actual and not that new standard deviation. So this is the standard deviation and mean. So you don't actually have to go to one of our stats. It gives it for you, gives it to you, and it tells you what your sample size is. Isn't that just gorgeous? Does all that for you? Okay, I'm going to show you now how to do it with the other one. I'm going to pop back to the last one that we did with the pennies. So once again, I'm going to go to stat, arrow over to tests, and go down to T interval. It's number 8 on mine. So I'm going to go to stats now and hit enter. Now it will automatically populate the stats from your list if you've already run this once, but that's not what we're using. What I'm going to use is the 2.64 or 2.464, which is what we were given for the pennies. And the standard deviation they gave us was 0.02. Remember, this is the actual standard deviation and not the new standard deviation. It does all that extra work for us. And our sample size was 17. Our confidence level was 0.99. So this is the stuff from the previous, from the pennies. Go down to calculate and hit enter. Bam. We had 2.45 and we had 2.478. Guess what? They have the same thing we do. So we did it right because we're awesome like that. Questions about the calculator? Okay. Give me a second to pop back over to where we were. All right. I bet you want to figure out how to find the sample size you need. Even if you didn't, we're going to do that. So this is our margin of error. I kind of gave you guys that separately yesterday for the other, or Tuesday for the other one. So I just kind of threw that there. So once again, we took this formula and we solved for sample size. So we just manipulated this formula and solved for sample size. Now, the issue we have when we're finding the sample size with mean is that we need a sample size in order to get our t-value, because that requires us to know how many degrees of freedom it is. Well, we're just going to, our cheat here, because remember we had a cheat before with the previous study. The cheat here is that we are using a z-score instead of a t-score, because the z-score is going to be close enough to help us with our sample size. So we're just going to use a z-score instead. So you can use that at the bottom of the z table where it gives you your z-scores, your critical values. That's what we're going to use. Okay, so I'm going to move over. Let's take a look. All right, so back to the pennies. How large of a sample would we need to estimate the mean weight of pennies manufactured after 1982 within 0.005 grams with 99% confidence? Our sample standard deviation is 0.02. They're giving us a population, or our assumption there. So they're saying our sample standard deviation or whatever is 0.02. So they're going to give us some assumption of a standard deviation. They have to. We can't find our sample size without some sort of an assumption there. So they're going to give that to you. So we're going to go back to our Z table. So go up to the confidence, the critical values for confidence level, or for, sorry, the critical values, 0.99, is 2.575. So that's what we're going to use. And I'm going to have to write it down as soon as I get over there. Otherwise, I'm going to forget it. 2.575. Okay, that's my Z sub alpha divided by 2. All right, so I would totally forget it. All right, so our N equals Z sub alpha divided by 2 times standard deviation divided by the margin of error squared. So N is going to equal 2.575 times times 0.02 divided by 0.005. That is our margin of error right here. That's what that within means. And square the whole thing. If you are careful, you can do the whole thing in your calculator at once. If you're careful. Times 0.02 divided by 0.005 squared. My approximate answer is 106.09, so we would use 107. Remember that we always round up. Please check my math. I don't trust myself. Let me know if you agree. You got that too? Oh, good. So we would need a sample size of 107. All right, let's do one more. Look at that. I guess I would just go to the next screen. So back to the miles per gallon. Okay, we need to know though what our standard deviation was. I hate when I do that. Standard deviation for the miles per gallon was 2.917. I'm going to write that down. 2.917. Our 2.917. Okay. So we want to know how large of a sample is it required if we want to estimate our mean miles within a half of 1/2 miles per gallon, 0.5 miles per gallon with 95% confidence. I think I'm going to jump back to the table and so we can at least get that. And then I'm going to have you work on this. So 95% is 1.96. So our Z sub alpha divided by 2, 1.96. So go ahead and get started without me and I will work quietly behind you. What do we got? I got 131. Yes, you did it. No, you did it. Yay! I got to tell you, I typoed like 4 times before I got it right. Before I messed up, like I kept putting random parentheses and weird spots in my calculator. So 131, good. Yay! It's awesome. Y'all are fantastic. So I think probably the most complicated part of the whole thing is the t-table, but once you start using it, it's not going to be too bad. You'll get the hang of it. Just don't forget when you're finding the critical value, you need n minus 1 degrees of freedom. But it's only for the critical value, not for the standard deviation. All right, so I think, is that the end of chapter 9? Nope. Okay, I just have a real quick recap here. I forgot I had these. So I want to show you the difference between today and what we did on Tuesday, just real quick, because I know that it's easy to get your wires crossed here. There are keywords. So the stuff that we did on Tuesday, you're going to see words like proportion. You look for the word proportion. It's going to be in there. So for Tuesday, that it's going to say proportion and it's going to have like percents in it and things like that. So there's going to be percents there. For today, you're going to see the word mean, plus you're going to have units. Proportions, you won't have units. For the mean, you're going to have units. For finding the sample size, important things you're going to get is something like within 3 percentage points. It's going to talk about how many percentage points you want to be between. So for the stuff on Tuesday, it's going to talk about percentage points. For today, it's going to say something like estimate within this many miles per gallon. It's going to talk about, and it will say mean. You're estimating the mean, but it's going to have your units there and it's not going to be a percent. So that's the difference between yesterday and today, or Tuesday and today. In my brain, it was yesterday. All right, so that is the end of 9.2. I'm going to do the lab. The lab is super quick this week. It is a very quick lab. I'm going to go to the lab and we're going to do that. And then after that, you can make the decision if you want to stick around or if you want to leave um, and just watch the video later. Will not hurt my feelings if you decide to bow out. Not even a little bit. Okay. So I'm going to pop over to the lab. For the lab, where are we? I have it. Okay, I know it. I minimized it. It was annoying me because it was in the way. All right. Okay, change our energy here. We're all playing with Excel. Got to get all nerdy. My nerdy hat on. For some reason, whenever I work in Excel, I feel like extra nerdy. I know I'm nerdy anyway because I teach math, but I feel extra nerdy with Excel. I don't know. It's just weirdo that I am. Okay, you should still have your descriptive statistics, when you are on your data tab, your data analysis, your descriptive statistics tools, I can't say it, should still be there. Hopefully you didn't turn them off. Now, if you did turn them off, just go back to, I think it was week 3, week 2, or week 3. And actually, was it week 3? I don't know. Go back to the beginning and find that video and do that and find them again because I'm not going to go through all of that again. So they should still be there. If you didn't turn them off, they're still there. So once again, we're going to be using the descriptive statistics. We're just going to change things up just a little bit. So I'm going to click on the data analysis tab and this stuff pops up and I'm looking for descriptive statistics. This is the same thing we did before. Once again, the data tab up top, go to your data analysis and you're looking for descriptive statistics. Then you click OK. I am using the continuous data from lab 1 that we used again in lab 2. Feel free to continue to use that continuous data. However, you never know if you have some good continuous data from your final project, you might want to just throw it in there and play with it. Who knows? You're absolutely welcome to use whatever continuous data you have. All right, I'm going to highlight all of this because this is my input. Remember, I have a million and 5 of these. So I am inputting in my input range. My output range is where I want it to live when it's done. So I have a box here. I'm going to highlight the box. That's where it's going to live. Okay. Things are going to change right here. We do want summary statistics. So click on the summary statistics box. The other thing we want, confidence level for mean, right there. I'm going to click on the box for confidence level for mean. You can make whatever confidence level you want. You can make it 99%, you can make it 95, you can make it 90, you could be really weird and do something like 82.5%. Whatever you want it to be, put your confidence level right there. When I click OK, it's going to populate. I'm going to make it bigger so that we can see it. And I'm going to zoom in a little bit. So all of this is the stuff that we had before, but now on the bottom, this thing right here that I just highlighted, that's your margin of error based on a 95% confidence level. This is your margin of error. All right. So once again, we're going to use our Excel tools to fill in boxes. So I'm going to click on the margin of error box, click equals, and click on that box right there where my margin of error is and hit enter. The mean, it's up there at the top. Once again, equals, click on mean, hit enter. For the lower bound, I'm going to take the mean and subtract my margin of error. So I'll do equals, click on mean, then minus, margin of error, and hit enter. It subtracted that for me. For the upper bound, you take your mean and you're adding the margin of error. So equals, click on the mean, hit the plus, margin of error, and hit enter. So this gives me my range of data, my range of my confidence interval right there, my lower bound and my upper bound. So your questions down here at the bottom are just kind of scaffolding. What am I estimating? It says in the context of the problem. So this is where you're basically telling me what your data is about. So I am estimating the actual mean magnitude of earthquakes in however many countries that I am looking at. So I am estimating the mean earthquake, the actual mean magnitude of earthquakes in the world. So whatever your data is, you're estimating the actual average of that. Don't put any numbers in there or anything yet. You're just telling me what you're estimating. You are estimating a mean, estimating the population mean. GPA, it's basically continuous. Yeah, it's continuous. Yeah, that works. Okay. How confident are you? All you got to do is say, I am 95% confident that the population mean is in my interval. There you go. Whatever your confidence level is, that's what you're typing in there. Even if you just said, I'm 95% confident, I'll take it. This number 3, I want you to type your entire conclusion. Number 3 is your entire conclusion. And remember, use your units. Reference what your data is. I'm 95% confident that the actual mean magnitude of earthquakes in the world is between 6.86 and 7.23. You need to actually reference what your data means and give me your conclusion. Those conclusions I've been writing on the PowerPoints, that's what you're referencing here. And that's it. That's your lab. And feel free to use use the data you collected for your final project if you want to. I mean, you could even include the confidence interval and just say, hey, we were doing confidence intervals and I found this curious. Even if it doesn't answer your question, I am okay with you as long as you explain, I was curious about this. I did this. Here's what it means. You're absolutely okay doing that. If you don't want to, that's okay also. But I'm just saying you can do that. Any questions about the lab? I know you guys watch this and you're like, oh yeah, that's super easy. And then you go to do it and you're like, wait a minute, I don't remember anything. It's I I understand. It's true, I know. This is why I do the best I can to answer questions. You already forgot the first half. I do that when I read novels. Have you ever done that where you read a few chapters and you put it down and you're like, I have no idea what my book is about? Yep. I'll pick it up and start reading it again and it comes back to me, but I frequently do that. I'm like, I have no idea what the book's about that I'm reading. And people will say, "What are you reading?" And I'll be, I'm reading this book. What is it about?" I have no idea. Okay, at least it's not just me. All right. Okay, so now, if you are planning to stay for 10.1, that's what we're starting right now. If you are not, you have a good night and I'll see you Tuesday. You are more than welcome to bow out or you can stay. It's totally up to you, but we're going to jump into 10.1. Once again, 10.1 has no math. Put your calculator down. You can sit back a little bit with just your pen, your paper and your pencil or whatever, your PowerPoint, but we're just going to go through 10.1. This is really great groundwork for 10. And 10's the last chapter. And by the way, I did unlock the homework already, just in case you want to get a jump on it. I did unlock the 10.1 homework. Don't feel pressured to do it yet, but it is there. Okay, so we're going to talk about hypothesis testing. Hypothesis testing, it does a really great job building on what we did in chapter 9. So we'll put chapter 9 in your pocket, but make it easily accessible because we might pull it out again. But it really builds off chapter 9 beautifully. So basically, so a hypothesis, it's a statement regarding a characteristic of a population. So um, I might, be taking a look going, people said this is the thing that I was discussing in my class, my AP pre-calc class today. So apparently 20% of all people can smell ants. I'm a person that can smell ants and it's really disgusting. And I was talking to my AP pre-calc class and I said, it's really gross. I'm one of the 20% of people that can smell ants and I think it's gross. And then you too, you can smell them too. Okay. So all these kids in my class were popping up saying, I can smell ants too. I can smell ants too. I'm like, that is way more than 20%. So my hypothesis would be, I believe that more than 20% of people can smell ants. I believe that the actual percent is greater than that. That's basically what a hypothesis is I kind of like, I haven't taken any data yet, but I'm kind of like, wait, there's a lot of people that are saying that they can smell ants. So I think it's probably greater than 20%. If you can't smell ants, you have no idea how lucky you are. Anyway, so that's what it is. So we have claims here. So you have to make a claim. So this is one of the claims. In 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So you don't even have to say it's greater than or less than. You just have to say, I believe it's not that. I believe it's different than that. So that's one. Here's another one. According to a study published in 2006, the mean length of a phone call on a cell phone was 3.25 minutes. A researcher believes that the length of a call has increased since then. So this researcher is saying he believes it's more than that. One more. Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces with it, but now there's new equipment. So quality control believes that the standard deviation has decreased. So this one is for less than. We are not going to do hypothesis testing with standard deviation. This is just an example. I mean, you can do it, but we're not going to do it. All right. So we we test these statements with sample data. It doesn't make sense to do hypothesis testing if we could actually poll the entire population. It wouldn't make sense because we wouldn't have to do any guesses because we know everything. All right. So what we do with hypothesis testing, I already kind of showed you or told you about it, is I'm observing things that make it seem like implausible that the actual percent is that. So basically, we will see like a statistic in the wild, and I'm like, my observations are different. So we will use sample evidence and probability to test our statement. So I could take a sample of a whole bunch of people and ask them, do you smell ants? And then I can test it and say, what is the probability I would have this sample with this answer? if the actual that 20% were true. If only 20% people believe or smelled ants, would I be able to get a sample that looks like this? That's what we're doing. We're looking at, is my sample unusual? We've been doing unusual for a few weeks, so hopefully that makes sense. And I'll obviously dive deeper once we're doing math. Okay, so here's how we do hypothesis testing. You make a statement. So once again, 20% of people can smell ants. I think it's greater than that. So what I'm going to do is I'm going to start polling people. I'm going to collect my data. I'm going to take a random sample of people and I'm going to say, do you smell ants? And I'm like, oh, wait, look, 38% of the people that I polled can smell ants. So then I'm going to say, what is the probability that I got a sample of 38% of the people in my sample were able to smell ants if only 20% actually did in the population? And then we would see, is it plausible? That's what we're doing here. So our null hypothesis, it is the statement we're testing. The null hypothesis is something that we are going to assume is true until we have evidence that indicates otherwise. We are going to believe that only 20% of people can smell ants until we have evidence to show it isn't that way. So the null hypothesis is true until you can prove otherwise. We use we use H sub 0. It's also called H naught. Anytime you have a subscript that's 0, it's called naught. So H naught is our null hypothesis. That is the symbol that we use for it. The alternative hypothesis. There's two different ways that they write this. It's either H sub 1 or H sub A. I see it both ways. I don't remember which one my open math uses, but both of them are used interchangeably. The alternative hypothesis is what we're trying to find evidence to support. I'm trying to find evidence to support that no more than 20% of people can smell ants. That's what I'm trying to support. That's my alternative hypothesis. Right. So this is important here. If we see the word different, it is a two-tailed test. If we say, I think it's different, it's called a two-tailed test because it could be greater than and it could be less than. So that is a two-tailed test because we're going to be looking in both tails. A left-tailed test is when we see like has decreased or less than or anything like that. So I'm going to go back up here because I'm going to draw pictures. So if I have a curve right here, it's basically we created a confidence interval. And if my sample data lands me out there or out there, then we know that our null hypothesis is not true. So with the left-tailed test, I have my curve, and we're only looking down here. We're only looking down here. If my sample data ends up down there below the curve, if it ends up in this tail, then we find out that our null hypothesis is not true. For a right-tailed test, you'll see something like has increased, these kind of words, has increased or greater than, or you can even say more than, larger, more than, anything like that. That would be a right-tailed test. So once again, I'd have my curve. That's an ugly curve. And we would be looking out here. If my sample lands out there outside that confidence interval on the right, then we would say that our null hypothesis is not true. This is essentially what we're doing. Any questions on this before we move on? And all this is setting up. We're not doing any math yet. Okay, let's do some examples. I think that's where we are. So the null hypothesis is our statement of status quo. So we believe the null hypothesis until we prove it wrong. We believe the null hypothesis until we have evidence to the contrary. That 20% stands firm until I have evidence to say, no, it is not true. So it's going to stand firm. Okay, so we're going to write our null and our alternative hypotheses, and we're going to determine what kind of a test this is. Okay. 62% of adults regularly volunteer their time for charity work. A researcher believes this percentage is different. So different is our key word here. Because it says different, this is a two-tailed test. Because it says different, it is a two-tailed test. The null hypothesis, when you write it, the null hypothesis will always be equal. So we do null hypothesis, colon, and we're looking at a percentage. So this percentage is a proportion. Therefore, we're going to use P equals 0.62 because the proportion of people who volunteer is 62%. So our null hypothesis, this is what we believe is true until we prove it isn't. Our alternative hypothesis, still going to be P, still going to be 0.62. Different means not equal to. So the only thing that changes is this sign. I'm going to write that. Only thing that changes. The number stays the same. The symbol stays the same. Well, except for the over here. But like the P or mu or standard deviation, the only thing that changes is the sign. Give you a second to write that down. We'll go to the next screen. All right. This is all the same stuff I just said. It's just they they like to give you extra words. So you have all the extra words on your PowerPoint. I've said it before. I think textbook writers get paid by the word. Prove me wrong. There's our hypothesis. Okay, here's the next one. According to a study published by, I don't know, by somebody in March 2006, the mean length of a phone call on a cell phone was 3.25 minutes. A researcher believes the call has increased. They believe it has increased. It says increased. This is a right-tailed test. Because it has increased. Our null hypothesis. We're talking about mean length of a phone call. So use mu. Always equals 3.25 minutes. Remember, the null hypothesis is always going to say equals. Alternative hypothesis. Everything is the same except the sign. So greater than says has increased. So this means greater than. That's a really ugly greater than, but you know what it means. All right. We're doing good so far. Make sure you interrupt me if you have a question. I get really excited sometimes. I love hypothesis testing. I know I say that about everything, but I really do love hypothesis testing. Okay. All of the stuff, Just a lot of extra words. It's all the stuff I just said, just more words. I don't think it's gonna, oh, it does do it with that. I don't have a whole lot of room. Using an old manufacturing process, the standard deviation of the amount of wine in bottles was 0.23 ounces. With the new equipment, they believe it has decreased. Has decreased. Decreased means less than. So this is a left-tailed test because it says has decreased. Look for those trigger words. So my null hypothesis, we're using standard deviation, always equals. If I emphasize something over and over and over again, it usually means that people forget it. Now, alternative hypothesis. That should be a 1. Everything stays the same except that symbol in the middle. Left-tailed test, so less than. We believe that the new standard deviation is less than. Now, another thing people forget a lot is they lose this symbol, this standard deviation symbol. Don't lose that. A lot of times they'll just say null hypothesis equals 0.23 ounces, alternative hypothesis less than 0.23 ounces. Don't forget the symbol for mean or proportion or whatever it is. Don't forget that symbol. Es muy importante. Right. Questions so far? Are we doing okay? Right. I know it's late. I know it says we have 14 slides left, but they go quick, especially since one of them is just this whole lot of words that say exactly what I just said. Okay. So I'm going to tell you, type 1 error and type 2 error are two of the more difficult things to remember. They're kind of confusing. I'm going to do the best that I can. So there's 4 different outcomes you can have from a hypothesis test. You can reject the null hypothesis when you figure out that the alternative hypothesis is true. That's good, because if the alternative is true, we reject the null. Do not reject. I like the words. I'm going to change the words here. I like the words fail to reject. I usually use the words fail to reject instead of do not reject, just because it sounds better. So if we determine that the null hypothesis is true, we fail to reject it. We will not reject it if we figure out it's true. Now, these are the 2 wrong ones. I'm going to put this right here. These are the 2 wrong ones. These are when you make errors, a type 1 error. So if we realize that if the null hypothesis was true, but we reject it, this is a type 1 error. So this would be reject when we shouldn't. So the type 1 error is when we reject when we shouldn't. That's a type 1 error. Uh-oh. Sorry about that. A type 2 error is if we fail to reject the null hypothesis when we should reject it. We figure out the alternative hypothesis is true, but we don't reject it. We don't reject the null. So fail to reject when null is wrong. This is the type 2 error. So if we don't reject it, but we should have rejected it, that's a type 2 error. If we reject it when we should reject it, that's a type 1 error. Now, I highly recommend like tabbing this page, putting a tab on it. On your next quiz, on the quiz 7, so I think it's quiz 7. Yeah. Quiz 7, so not quiz 6, but quiz 7, you're going to have a question about which type of error it is. So tab this page. And I can guarantee on the next test, there will be a question about type 1 and type 2 errors. So tab this page because this is going to be helpful. So put a tab there. I'm not in the business of being sneaky. Try not to be anyway. Even though I liked the bonus question on the test. Tell you, Bobo and Chachi, those I had my favorite professor in college. He used to use those whenever he made up an example off the top of his head. He'd make his characters Bobo and Chachi, and so that was kind of a nod to him. He's really an amazing teacher. He's retired now, though. All right. So let's talk about what a type 1 error would be here. So remember, type 1 error is reject when we shouldn't. So if we determined, so, uh-oh, reject when we shouldn't. So if it's determined that, well, that 62% of Americans volunteer, but we reject the null, I'm just going to put next here type 1 error. 1 error. And then the other one was fail to reject when we should. If it's determined, if the actual percent is different than 62%, but we fail to reject. It's a type 2 error. Okay, I'll give you a second to write that down. We really probably only have maybe 8 minutes left and we'll be done. Y'all are fantastic for hanging in. I know these are hard. These are hard to understand. I get it. This is a tough one. Okay. Can I move on? We good? All right. So this is the exact same things I just said. I'm going to just move on. This is the exact same things just written out, probably fancier words. We're going to do one more. Okay. So mean length of a phone call. We want the type 1 and the type 2 error. So type 1. So type 1 was to, okay, reject when we shouldn't. Okay, so yeah, that's why I let you use notes because I can't remember things. So, actual length of phone call of a call is 3.25 minutes, but we reject the null. Okay. Type 2 error. Type 2 error is when we fail to reject, but we should reject. Actual length of a call, it should be mean length, but I didn't write that in there, is greater than 3.25 minutes, but we failed to reject. There we go. I'll give you a minute. So hopefully that unmuddies the water just a little bit. But definitely tab that page. It'll be helpful. Questions on type 1 and type 2 errors before we move forward? Okay, we're going to talk about the probability of these errors, but we're not going deep. We're definitely scratching the surface. Okay. The probability of a type 1 error is alpha. That alpha that we use in our confidence intervals in our hypothesis testing, that is the probability of a type 1 error. The probability of a type 2 error is beta. Now, on your quiz 7, it's going to ask you what type of an error is it and what is the probability of making that error. If it's a type 1 error, you're going to say this is a type 1 error. The probability is alpha. That's all I need. If it's a type 2 error, you will say this is a type 2 error. The probability is beta. That's all I need. Do not get more complicated than that. Probability of type 1 error is alpha. Probability of type 2 error is beta. That's it. You don't need numbers or anything. Don't get fancy. Now, if you go on to STATS 244, which very, very few people do, you're going to have to go a little bit deeper here, but we're not in 244. We're in 243. So we're just leaving it at that. They'll go deeper on a lot of stuff than I do because this is an intro class. And you don't necessarily, this, as the probability of making, they will give you, sorry, we figure out the probability of making a type 1 error before we start, but you don't have to figure that out. They will tell you. They will tell you what your level of significance is. They will tell you what your alpha is. The alpha doesn't matter right now because we're not doing math yet, but you will be told what that is. You don't have to come up with it. But our alpha that we're going to be using is the probability of making a type 1 error. And as the type 1 error gets bigger, the probability of type 1 error gets bigger, probability of type 2 error decreases. You don't need to remember this. Nobody's going to mention it again. So just kind of nod your head and smile, and we will move on. All right, conclusions. Oh, no, I forgot the screen. We never accept the null hypothesis. You either reject it or you fail to reject it. Kind of like we never say the defendant is innocent. We say they're not guilty. We never declare anybody innocent. We just declare them not guilty. Same thing. You reject the null hypothesis or you fail to reject the null hypothesis. That's it. You either reject or do not reject. I don't like the words do not reject. You can use them if you want. I don't use them. I say fail to reject. But regardless, you either reject or you fail to reject. We do not accept. I do not accept it. So anyway, okay. We are going to write conclusions. They use a heck of a lot of words in their conclusions. I don't use quite as many words in my conclusions. Now, we are going to have more information to write the conclusions when we're actually writing them, but we're going to just give you some super simple ones. I'm just going to go through the ones that they give us because I'm going to be altering them just slightly. So our sample evidence indicated that we should reject the null hypothesis with the phone calls. So here's their super long way of writing this. The statement in the alternative hypothesis is that the mean call length is greater than 3.25 minutes. Since the null hypothesis is rejected, there's sufficient evidence to conclude the mean length of a phone call is greater than 3.25 minutes. Here's mine. I just say there is sufficient evidence that the mean length of a call is greater than 3.25 minutes. So we reject the null hypothesis. So see, that's less words. Oops, I spelled hypothesis weird. Okay, that's less words. I don't feel like you need to completely restate the original claim because you've written it all down. So you don't have to restate the original claim. I feel like this is completely adequate, and since I'm the one giving you a grade, you can agree with me. If you like more words, go for it. Right? Got one more. I think that's it. I think we have one more. Okay. Yep, it is. We're on 57 and we have 58 slides. Suppose the sample evidence indicates that the null hypothesis should not be rejected. So we're going to state the wording of the conclusions here. Once again, they have a ton of words. I'm going to show you mine. There is not sufficient evidence to support the mean length of a call is greater than 3.25 minutes. Therefore, we fail to reject the null hypothesis. Bam. That's it. Oh, something weird happened. There we go. That's it. It's our night. I know we went late, but y'all were fantastic. I'm glad that we got this out of the way. It'll make Tuesday a little bit easier because I was not about giving you guys 3 sections in one night. So I was not about that. I'm sure you guys didn't want 3 sections in one night. So we are still being recorded. Any questions for on the recording? Okay, let's stop the recording. That's not the right word. There we go.